Thanks everyone for coming to this 9th and final lecture of IAP. Thanks to all of you who have stuck it out and those people who have joined us remotely from MIT. So today I'm going to talk about, can LLMs do math, which is something near and dear to my heart as a former mathematician. No. No, I have a better TLDR than that. I think that they cannot prove interesting theorems on their own yet, but they can already help us verify interesting theorems. And that may hint at the type of math I'm going to be talking about today, which is proofs. I'm not going to be talking about adding things. So let's get started. Okay, as I said, proofs. And I'm going to get into some different approaches and speculations about having LLMs do math. Okay, Gulan has posted a live stream link. So there's one from DeepMind called FunSearch. Another one from DeepMind called AlphaGeometry. And then there's been this really interesting effort to formalize a big math conjecture. And I want to hopefully talk about all three of these a bit. And there will be Formula A. Okay. So again, not multiplying, not writing algorithms. Yes to proving that square root of 2 is irrational. Back in the early days of ChatGPT, like day 2 that it was available, all of us were trying to get it to prove that the square root of 2 is irrational. And it could not do it. It looked really convincing, like it was like, let A over B equal 2, and then do all this stuff that looked very convincing, but then it would be bullshit. But it definitely can do it now. It's like, it's memorized all the classic proofs by now. Like, I was not able to trick it on any reasonable little proof I had seen. But today I'm going to be talking about proving new stuff. So what's different between proofs and like the other stuff I was talking about, computation and algorithms? So in general, computation is not something that we can be sure is correct. All we can do is measure the accuracy of the LLM that we've trained to do the thing. But we don't know for sure that it's going to be correct. Math, on the other hand, is different. If you write a mathematical proof correctly, it cannot be wrong. Okay, I have an asterisk here because that's what it's supposed to be like, but really that's not what it is. This is what math is supposed to look like. But as you can see, you have to write quite a lot to prove that 1 + 1 = 2 if you prove things in first order logic all the way from principles. And in reality, mathematicians write they program in a high-level programming language called grad student, which is not really formally checkable. So morally, math is supposed to be one of these problems where solutions can be checked easily, but not necessarily found easily, like NP. You can, it's an exercise to the listeners to say why math is not really an NP, but morally, it's kind of like that. Yeah, so finding a proof is super hard. That's why we have prizes and famous people, but checking proofs is not supposed to be hard. And LLMs could help us with either or both of these things, basically the search and the verification parts. So recall from the planning lectures that basically LLMs can help with 2 aspects. They can help us with looking, like finding creative directions to look, and they can also help us with evaluating and verifying like states that we've reached. So there's, I think, like 2 approaches for LLMs in math. One is to use them in the search to actually have them provide the creativity. That's what AlphaGeometry and FunSearch are doing. And then there's using them in verification. And that's where people have used LLMs a bit to help formalize this big theorem, which I'll talk about. So let's talk about search first. So the recipe for this is basically pick a particular type of problem with a sort of crux where verification is easy. So it's like, I've done all this sort of, I've done all this groundwork, and now I just found this one part where I've got to find something, and I can easily check if that thing is good or not. So you use an LLM or a model to basically search for a solution to that, and you reap an incremental reward. So in my mind, these things are very cool that LLMs can do this better than humans. However, it's not quite as cool as doing new math altogether. So here's FunSearch. This is DeepMind's first paper on this. So mathematical discoveries from program search with large language models. So from this alone, this architecture, you can't really tell how this would be doing math. But basically, there's some sense in which they are writing programs which can sort of prove math theorems. But the basic architecture is actually really more of a like a coding prompting architecture. So you have a specification, you first turn that into a prompt, it goes into a pre-trained LLM, which spits out a bunch of programs for you, maybe like sorting algorithms or whatever. Then you have some evaluation, which can also often be like cheap automated stuff, like how fast did this thing sort? Then you put that into a programs database, and then they do something called they call best shot prompting, which is basically you take the highest scoring things out of the database and put them back into the prompt again, and then have it create a new one by sort of synthesizing the best parts of those programs. All right, so how does this do math? So let's look at the problem that they solved with it. It's called the CAPSET problem. And if you don't find out what this problem is, even after these slides, that's fine. You don't need to know what it is to understand this, but I'm going to talk about it anyway. So a CAPSET, it's a set of vectors in 0, 1, 2 to the n. So basically like integer vectors mod 3. And this set has the property that no 3 of them should sum to the 0 vector. So this is an example in for n equals 2. So you could think about this as a 3 by 3 grid, right? 0, 1, 2, 0, 1, 2. And this is the 0 point right here. And these blue vectors here, no 3 of them sum to 0. So that's a CAPSET. And the question is, in general, what is the size of the largest CAPSET in dimension n? And you can try to convince yourself that it's between 2 to the n and 3 to the n. Like obviously it's less than 3 to the n, that's how many there are. But why do we care about this? Basically because Terry Tao likes it, and he's smart, so that's why. Realistically, like DeepMind people just needed some problem to show they could do this, and this is a good candidate. Yeah, so this is this fancy looking thing, but it's basically, we don't care about, for a particular n, what we care about is as n goes to infinity, and basically we know that this number is growing exponentially, so we should raise it to the 1 over n to get something sensible. And basically a bunch of clever human labor has been used to find a specific type of CAPSET that can be bootstrapped to provide a growing family of CAPSETs for all n. So basically, there's a finite search problem, which solving this finite search problem will give you a bound on something for all n. And what did they do for how did they use FunSearch to solve this? Basically, the LLM searched for programs that were constrained to output these admissible CAPSETs. So they would keep iterating on programs that would produce CAPSETs, and they had like a particularly nice way of constraining it. All they did was the program just specified the order in which you would add points to the CAPSET, and then you just, as soon as you hit something that's not admissible anymore, you stop. And then the eval is, well, how big is it? And that's it. And they beat human bounds. But like, as you can see, like these are just numbers that are between 2 and 3. It's like we already knew it was bigger than like 2.2, and I think the upper bound is like 2.7. So we get these sort of incremental rewards from letting AI do it. Still, I think that is interesting because it's an interesting way to narrow down a search space. Because basically, if you think about what all the cap sets are, there's 2 to the 3 to the end of them. You can't search through that. So you actually search by searching for a program to generate them. So like you're searching over low complexity elements of the search space. And yeah, there's this XKCD which explains Kolmogorov complexity pretty well. Just basically the shortest out program you need to output something. And this kind of approach makes sense because A, like LLMs are good at coding, and B, well, just some set is not very informative. It's better to know how you made it. And these guys claim that, which I don't know if I believe, but they claim that like looking at what functions this program came up with gave them insight on cap sets or something, which that is sort of hopeful in my mind. Yeah, so the TLDR is, after lots of human effort to find a way to bootstrap some finite thing into an infinite thing, LLMs can help you search for the finite thing. And it's sort of in keeping with like using LLMs to get, or deep neural nets to give a little bump on some poorly modeled part of a problem. So like we saw it in a previous DeepMind paper about faster matrix multiplication, stockfish, and some of the approaches to differential equation solving with deep nets too. Any questions about FunSearch? All right. So next onto AlphaGeometry, which I think is cooler. So this was in the news recently. Basically, they were able to train a model that could almost hit gold medal level on IMO geometry problems. I think this paper is so cool. Like, not just the LLMs part, but like all the technical work that they had to do to get this to go was like very, very cool. So what is AlphaGeometry? They're solving IMO geometry proofs, and the model is it's kind of similar. You use an LLM to propose proof steps, and then you use symbolic deduction to see if the conclusion you want is reachable, and then you iterate this. And I think one of their big innovations was that they heavily used synthetic data to train this LLM to propose these proof steps. So here's like what it looks like to do an IMO geometry problem. Okay, this is not as hard as an IMO geometry problem. So the problem we have here is let ABC be any triangle with AB equals AC. So these two sides should be equal. Prove that this angle is equal to this angle. So the ultimate solution that you can come up with is construct the midpoint of BC, and then you do some sort of like symbolic reasoning here to deduce that BD equals DC, and then like you end up with your conclusion. But the main thing is that there's the way that the solutions to these problems often go is that you have to construct some new point that wasn't given to you in the original problem specification. So those are like what they're considering to be the creative steps of an IMO problem. So that's the way it goes. You construct some new points that aren't in your original thing. You do a symbolic deduction to see what you can prove from that. Like if your conclusion is in there, and you're either solved or not solved, then you just loop. You do a new construction every time. So this slide is just a longer version of that. They wrote a new symbolic engine to do this basically this symbolic reasoning part. And I think if I interpret the paper right, like their symbolic engine is already better than any automated theorem proving thing that anyone has written already. So it's like, I don't know, I think that's pretty awesome. But yeah, this is just a side note, is that like they had this formalized language that they use to basically express theorems and constructions and stuff. And humans have to translate the problem statement into that formal language. And actually, the formal language doesn't have full coverage of all IMO problems. It's only like, I think like 80% of geometry problems can even be expressed that way. Right, so here's a more complicated example. Yeah, like this is what a real IMO problem looks like. And like I can barely read it. But these are the actual stuff that you're given at the beginning. And all this blue stuff is like new points, lines, and circles that AlphaGeometry came up with to get the proof. And the black stuff is all symbolic deduction engine. And then finally, they did find out that that the conclusion, that's tangency conclusion, is in the result. No, it's purely like the prompt is like this formal proof language plus the symbolic reasoning steps. There's no vision. Yeah, so I think there's an ablation to see how much training helps, but the training is what got them the most mileage. And what they did is they used this formal sort of language that you can express these geometry premises in to sample random theorem premises. So what I'm telling you now is how to generate synthetic proofs that you can train to be able to prove real stuff. So they use the symbolic engine to prove a bunch of random stuff from these random premises, like kind of like just prove everything you can prove. And then they would sort of take away all of the stuff, like all of the premises that were not used by the symbolic engine in some sense. And those would be the auxiliary constructions. And this to me is kind of confusing, but basically they have like a really sophisticated algorithm to figure out what premises you do and don't need. And then basically the premises that you don't need are taken as part of the output of the training data. I'll explain this a little better one day. Okay. Yeah, so this is just like a pictorial version of this. Basically, like they sampled this sort of random shape with like a couple of random properties, like, oh, this is perpendicular, this is like some orthocenter, whatever. Then they just proved a bunch of stuff, and then they figured out that like certain conclusions that these the assumption that, I don't know what assumption this is, but some assumption about this thing. Oh yeah, maybe this assumption that that this foot is perpendicular to this BC. This was not used in this proof. So they were able to say, okay, that's going to be one of our constructions that we should train the model to produce. So basically, we have an inference LLM plus a checker and a loop, and we have some synthetic data, which starts with this forward process of taking a premise plus constructions. These are like unneeded premises, basically, and eventually goes to a bunch of conclusions. And they use that to create this data set by basically, this is what you get from your synthetic data. You take the premise and the conclusion and you try to create the constructions. So this part is easy to create, a premise plus a bunch of constructions to conclusions, but a premise and a desired conclusions to a bunch of constructions is hard, that's like what proving is. And that's what they trained it to do. A note is that like it still required a lot of human innovation because of these things being state of the art on their own, and it's also in a super constrained setting of IMO geometry problems. In my mind, there's a bit of a lesson for NLP here, which is like synthetic data could help if you want to model the inverse of a cheap but messy forward process. Like the forward process of humans saying their email address and making a bunch of ASR errors is easier than writing an algorithm to invert it. So like this process, like this is what we want to learn. It's easier to go the other way. Like I think it's harder to go from David spelled normally, then D as in dog, A-V-I-N, and then an A and I at gridspace.com to this. I think it's easier to go backwards in my mind. Okay, questions about AlphaGeometry before I go on? Yeah.
I don't know that much about the state of the art of like automated theory proving in general. Just like using that same sort of like constructive rule of inference and like pre-search, was it already the case that like traditional algorithms were able to do that, or was that like in and of itself like learning aside like really groundbreaking?
Yeah, maybe Anthony, can you restate it again? I'm not sure if I understand.
The machine learning step for doing it quickly aside was doing that sort of automated proof search search for Euclidean geometry already a thing, or was that in and of itself?
There were engines for doing like a certain amount of automated search, like from a construction. Like I think the hard part is to come up with like a new point. I need to place like a midpoint on this line, and then to do stuff from that. But they like, I guess, you know, I don't know if this is how it went, but I can imagine you're like, oh, like let me train this LLM to do this, but then you realize like I'm not getting state of the art. Like let me like also improve this symbolic reasoning thing. All right. Any other questions about it? So now I want to talk about the other direction. How can LLMs help us formalize all of math? So there's this, yeah, maybe I'll talk about it. So we just saw some sort of specialized context and some incremental solutions where LLMs could help, which I think is really awesome and hopefully promising. But we're not proving big conjectures with these things yet. And in my mind, I'm wondering like why we have to let the LLMs have the ideas. Like, let's make them do the boring part of formalizing our ideas. And I guess one of the problems with this is that not even human mathematicians do that. Like nobody was formalizing anything until super recently. There was a huge conjecture proven by, of course, Terence Tao and some other really smart people. People are calling these folks the A-team of math. Yeah, so we don't need to know what this conjecture is to talk about this, but if you're interested, it basically says that if you have like a bunch of mod 2 vectors that's closed under addition, that's close to being closed under addition, then it kind of has to look like a bunch of affine spaces. But it's not that important. And the point is that they were able to prove this kind of relationship to the degree that the conjecture required recently. Which, okay, yay, like mathematicians prove something. But I think what's cool is that only 1 month later, this thing was formalized. And this is a really neat blog post about Terry Tao talking about his workflow. Thanks, Lokman, for sending that to me. And they're sort of, these mathematicians like stack for doing this was Lean. It's a formalized proof language. this tool called Blueprint, which is like basically you can turn a math paper into like a directed acyclic graph of all the theorems and lemmas and definitions in the paper. And then they just use like a big chat and GitHub Copilot. So that's actually the only place that LLMs are currently entering to this story, is that they literally, like, while they were trying to code in this formal language, they had GitHub Copilot like suggest the next line for them. And this is, I don't know, this is only Terry Tao's story. Other people may not have done it this way. But, so this is what a blueprint looks like. It's got all these like nodes, which are theorems and lemmas and stuff, and it's color coded based on certain like properties, which I'll get into later. But like the goal is to get down to this node down here to turn it green. And you know, a month later, it was all green, and I guess it got redrawn as well, some graph drawing algorithm. So okay, what's lean? It's a formalized language, so you can sort of prove stuff through functional programming. I have to admit, like, I truly have such a hard time understanding lean. Like, I was hoping I would like learn a little bit of it for this talk, but it was hard. So just say it's a programming language that lets you prove stuff. But I think what's cool is that it's sort of a community effort, and there's a like expanding repository of like all math from the ground up proven in lean that you can use. So you can just like be like, I want to import this field, and I can use any theorem from that field. And then it does have a little bit of like symbolic reasoning magic that it will apply for you. Like you can be like, let me apply this lit arith tactic, which will deduce stuff like, if I have this and I want this, like that will just be taken care of for you. And I guess this sorry is what it tells you when like you're not done yet. Yeah, and there's like just a kernel, which is like very sort of simple trusted code, which is checking that that these proofs are true or not. So what does this formalization process look like? So as I was saying, you turn your paper into this directed acyclic graph, and then you sort of use your Discord or Zulip or whatever for people to just pick nodes, and they can asynchronously like work on all these steps. So you have to formalize the statement of the node. So maybe I should say like this definitely requires experts. This is like Terry Tower, Freddie Manners, like taking their paper and being like, how do I split this into pieces and parts and like label these nodes with theorem statements and proofs. So once an expert takes care of that, then sort of like grad students or whoever can, or maybe LLMs can do this part. So you have to formalize the statement. You have to formalize the ancestor statements, right? Because ancestors are like stuff you need to prove this node. And then you can actually formally prove them from the ancestors, and then finally you can be proved. So once the final polynomial Freiman-Rugen node is in the DAG is proved, then you're done. And they did it. But what's the takeaway? One of the takeaways is that this mathematician, Terry Tao, like one of the best mathematicians of our time, is very bullish about LLMs. So he thinks like you could sort of make these blueprints automatically from archive papers and automatically like try to prove stuff in lean, and then go back to, you know, blueprints, and then you could go from the blueprint to English or LaTeX or whatever. So maybe there is some hope for LLMs formalizing things. He also just like uses GPT to help him prove math sometimes, although he's like, you know, not that much. It's like sort of took some of the easy kind of stuff off his plate, I think. And this is huge, sorry. But basically somebody is like, this is a different, somebody from a different field, like I think algebraic number theory paper, they're saying like this field called additive combinatorics was a good candidate for this kind of stuff because you didn't need very much to formalize it all from the ground up. Actually, I think all that they used was entropy theory in this whole paper pretty much. And yeah, ultimately they ended up like contributing a lot to this Mathlib library because they formalized all of like sort of finite probability distribution entropy. But like a lot of fields just have like hundreds of years of work that we are going to have to slog through if we want to formalize them, which I would like LLMs to do that. But, okay, so questions about this PFR formalization effort? All right. So now I'll start pontificating. Like, should mathematicians be freaking out? And like, what is the point of it all? Like, is there even a point if LLMs come in and prove all this math? This is how I think it works now. Like mathematicians, they have these conjectures and they keep trying to prove them. And some of these things are really hard and they take like 30 years. But throughout the time, all these different things that different fields of math are trying to prove, like communicate with each other, get interconnected, and we get this big picture. And then like every once in a while, like some of these lower level parts will pop into the applications. Like we all know how to invert a matrix now in our, NLP land. Like we can multiply matrices, but those were from way down here in history. And then those things kind of feed back into the conjectures, and the theorems feed back into the conjectures and stuff. So like, I don't know. I'm not sure like, if a couple of these, like a bunch of these errors are replaced by LLMs, are we still going to have this kind of good idea, communications and all that? I don't know. Yeah, so like, this is my opinion about what the point of math is. Partly, it's nice to know things for certain, but it's much more nice to figure it out in a way that sheds light on other fields and neighboring fields and stuff. And like, if you try to just let LLMs like conjecture and prove all of the results, you might not really gain that much from math. It might be pointless. And we're not there yet. Like in my mind, they're not really proving real conjectures for now. Yeah, so that's it for my talk. Any questions before I get into exercises from last time? Yeah.
So now we have compared to human, like they're proposing conjectures.
I don't know. I mean, I do know that like there was some interesting things happening in the AlphaGeometry paper, for instance. Like one of the things that happened is that AlphaGeometry was trying to prove one of the theorems, one of the questions, but basically they proved it, and then this traceback algorithm figured out that actually one of the premises in the theorem wasn't needed. So they actually came up with a new theorem because they just didn't use part of that theorem. So they did generalize a theorem on its own. Oh, sorry. Lokman said, how do LLMs perform at conjecturing as opposed to just proving things that people have already conjectured? The main answer is that I don't really know. Yeah, my guess is that without a lot of prompting, they wouldn't conjecture stuff that was interesting. But yeah, Anthony.
I saw a talk a year ago from someone who was working on the team, and he was posing the question: are theorems source code or are theorems literature? That's the way he put it. And he obviously was on source code because it works for me. I love like math textbooks. I love like reading like good, like kind of like Rich used to say, like the ones that are in the book.
The book, yeah.
Yeah. Do you think LLMs, even if they are not good at coming up with conjectures, they might almost find better proofs or better ways of presenting proofs?
So the question is like, are LLMs, could they help us make existing proofs more beautiful or find beautiful proofs? I'm not sure. For now, they're finding uglier proofs for sure. Like
Yeah.
apparently the alpha geometry proofs are like 20 times longer or something like that than the IMO students, but they get there, like they chug it out. So like, I don't know, unless we have some sort of like aesthetic scoring of these things and encourage them to do the right things, they probably won't. Yeah. Other questions? Okay. Exercises from last time. What is the rule of fucking insertion? And the rule is that fucking can be added before the primary stress of a word. Massachusetts. I guess Fulan, it can't be the first one, right? That's cheating. Like I can't just say fucking Massachusetts, but any other like stressed syllable, I guess is fine. I don't know. And the other exercise was, how would you define if an LM is memorizing data set, and how few parameters would you need to be confident it wasn't memorizing it? So in my mind, like, it doesn't make that much sense to say that a model is memorizing a single data set. Like maybe it just learned it. Like if you're training it to do addition, like maybe it didn't memorize those numbers, maybe it learned how to add. But it does make sense to talk about memorizing a family of data sets, like the famous paper where they showed that the vision models can memorize. They showed they can learn random labels on those images. Basically, like how many parameters would I need to believe that I was learning something would be at most log base 2 of the number of data sets that the model can learn perfectly.
When we started off, we picked 4 things that people can do that a raw LLM does not seem to be able to do. So planning, memory, perception, and language and symbolic reasoning. And so we did a pair of lectures on each of these, or I actually did 3 in the last. And if you were to draw some like broad conclusions, there are a lot of recurring patterns, right? So a language model really is just doing one language task. But a lot of times when you augment it with other algorithms, whether it's search or the ability to do proof solving like we saw today, or giving it access to a vision model, that you can take advantage of language models as a transducer, as a translator between any natural language system, whether it's a dialogue or a document, and the world of algorithms. And while there, I think, are a lot of things that we saw in all 4 of these categories that I would still consider, you know, unsolved or that have a lot of room to progress, compared to just being in the dialogue of a language model that is left to its own devices, you're with a good and sometimes well fine-tuned language model, maybe 1 or 2 steps away from doing stuff that's pretty remarkable, like having a conversation with something that has vision, or having a computer start to discover new math. And so I told the story on the first day from Arabian Nights of the man who tricked the genie to go back in the bottle, right? This genie of incredible power, but still could be easily outsmarted. And then he kind of got the best of both worlds, the power of the genie, but was able to keep it under his control. I think what we just saw was 8 lectures on how we have this powerful genie, but we can actually make it do useful work as long as we can get it back in the bottle. And so I wanted to wrap things up. So first, you can always continue to engage with us indefinitely by messaging IAP@gridspace.com. This is our 2nd time doing the IAP series. We'd love to get your feedback. I think Fulong might do a formal survey afterwards, but in general, we'd love to hear your feedback. We also might do a series in the summer for folks that are interested in it. Hey, buddy. And if you aren't already, please subscribe to our YouTube. All these videos were posted on YouTube, or maybe that's where you're watching it. And also follow us on Twitter and LinkedIn. So some upcoming recruiting events. So we're going to be at MIT actually in a week. So come visit us at MIT on the 9th. at the X Fair. We'll also be at Stanford for the Spring Career Fair in April. And then we'll be hosting LA office visits in the spring. And you can always, if you're interested in internships or a job, reach us at hiring@gridspace.com. So thank you very much, everybody.
Hello, thank you for calling Gridspace's YouTube channel. Did you make sure they liked the video and smash that subscribe button?
Yes, I did.
And ask them to leave any questions or thoughts in the comments. It helps me a ton. Thank you for watching, and if you'd like to talk to me yourself, go to gridspace.com and click on any one of our demos. Thank you, and talk to you soon.
Thank you, Grace.